Hey, business calculus. So today we're going to go over the derivative and what that means. But first, what's very important for the derivative is that we talk about the tangent line. Now, a tangent line is a straight line that touches a curve at a point, and you can say points or goes. We'll just use the word points in the same direction of the curve at that point. So if you have a curve like this, a tangent line, it touches it at that point, and at that point it goes in the same direction, right? That's what a tangent line is. And so here's another one right here. You notice how the tangent line is going in the same direction. And then once again here, it goes in the same direction. All right, so those are three tangent lines for that one curve. So you note that any particular curve has an infinite number of tangent lines, but the important thing is that it touches the curve at that point and it goes in the same direction. All right. So let's go on. Let's go ahead and say slash goes. A secant line is a straight line that intersects a curve at 2 points, right? Because you have these 2 points to define the curve. And if these 2 points are, well, before going into that, let's take a look at the secant line. Here is our line, and so the secant line, we have point 1, and then say point 2, and so the secant line is defined by these 2 points, like so. And I can pick any 2 points, doesn't matter, but that as long as the line intersects those 2 points. Now, what happens if I take this second point here and I start bringing it close in? If I start bringing it to where it slams in real close to the first point. Well, what happens then is that we have a line that's starting to look an awful lot like a tangent line. And so we can say that if these 2 points are close together, then the secant line resembles a tangent line. Right? That's how that works, right? We can use a secant line to approximate a tangent line so long as the 2 points are sufficiently close together. All right, so with a different colored pencil, draw a line tangent to the curve at 3, 1. So again, we're drawing a tangent line right here at this point, like so. And I'm just hand drawing it. I know it's not perfect, but it's close enough. All right, so there's our tangent line. Let's go ahead and take a look at the slope of this line. Right, we notice it falls down 1 and it runs over about 1/2. So let's calculate the slope of that tangent line. Well, that's going to be, again, it's rise over run. And so we know the rise is -1 because it drops down. And then the run over is simply by 1/2 units. And this can simplify up to -2. All right, so for this next bit, we're going to be drawing secant lines. And we're going to try and find a secant line or see how the secant line gets closer and closer to that tangent line. So first thing, we're going to draw one between 3, 1, that's the first point, and 6, 4. So that's here. And then we draw that one. We notice this looks nothing like the tangent line. And when we calculate the slope of that line, we're going to end up with something very different, right? So we rose up 3, and then we ran over 3. So we got a slope of a +1. That's a very different looking slope than the -2 that we're looking for. All right, so let's pick a point a little bit closer. Now we're going to 5, 1. We plop that point right here. And we notice with this guy, well, it's just a straight line, a slope of 0. And so when you calculate this one, indeed, that's exactly what we're going to have for the slope for that particular guy. It rise over run, we rose nothing, and then we ran over 2. 0 divided by 2 is 0. Okay, next one. We're bringing it down to 4, 0. And we notice this is already starting to look a lot closer to that line. Let's see the slope of this guy. We finally have a negative slope, so that's already an improvement. We fall down by 1, and then we ran over 1. So negative 1. We note that's a lot closer to the slope that we had before. And you can see, obviously, if we kept going closer and closer, we would indeed have a slope that was very close to the negative 2 over here. All right, so this next one, we're going to start looking at points from the other direction now, starting with D. 3, 1 as we've been looking, but now we're going to look at 3, 1 and then 1, 3. All right, so 1, 3, that's that point right here. Let's go ahead and draw that through. Starting off negative, which is good since our initial slope was negative, and so when we calculate this through, rise over run, looks like we fall down 2, and then we run over 2. So we're already starting off in a much better place. And so for these next 2, we're getting even closer and closer. I'll go ahead and leave these up to you guys to practice on your own. We kind of have an idea of how this works now. And you're just subtly bringing that point in closer and closer to the point 3, 1 to get an idea of what the slope for the tangent line is. And so the big takeaway here is that we're using a secant line to figure out the tangent line at a point. Alright, so this next part, note that the slopes of the secant line gets closer to the slope of the tangent line as both points get closer to each other. Okay, and so that is the big royal takeaway of this whole part right in here. Okay, now let's go ahead and look at a physical example. I know this is business calculus, but a little bit of physics does kind of help us see what's going on, and we're not going to get very deep into it. All right, so we're going to start with by trying to find the slope of the secant line between 0 and 4, then 0 and 2, and then 0 and 0.25. So let's go ahead and start off. 0 seconds and 4 seconds. Well, the secant line goes like this. Clearly for part A, the slope is 0. Okay, now let's go ahead and look at B. Now we're looking between 0 and 2 seconds. So at 2 seconds, we're up here. We draw our secant line, and so it's kind of telling us a little bit more about what's going on in between those two instances in time. You calculate the slope. Looks like we run up 3, and we run over 2. So positive slope of 3/2. That looks more like what's going on with that picture, but let's do the next one. C, where we're going between 0 and 0.25 seconds, and we're just going to eyeball this one. So put that one about right here. And you notice even when we draw this line, it seems to be going right on top of the curve. I'd say that's a really good estimate for what we are about here. And so, let's see, it looks like that's probably about 3/4 of the way up. So our slope here, rise, looks like we rose up about 3/4 of a meter. And we ran over 1/4 of a second. So that's 1 divided by 4. And that reduces to 3. So I want us to think about the units of each of these, right? We rose, which, the y is in meters. So we rose up 3/4 of a meter, and then we ran over in seconds, right? So that was on the bottom. Meters per second. Meters per second. So what is the physical meaning of these slopes? average velocities. And we're using those to approximate what we consider the velocity at the instant that this thing begins to move at 0 seconds. Okay, so now we're going to find the formula for the slope of a secant line. And so in the book it talks about this as being the average rate of change, the average slope. But these are all different ways of explaining the exact same thing. So let's go ahead and run through this. And as you're working through this, you should have a feeling that, even though I am giving you some guidance, it's something that you could have come up with on your own, just by kind of thinking through things logically. At least that's what I'm trying to imbue with this lesson. So try and think through this. Don't just mindlessly write down what you see me writing down on the screen. Try and really think through what's going on. And if you have to press the pause button and to kind of like get your bearings right, that's fine. That's actually one of the advantages of holding class this way. So with that being said, let's go ahead and move forward. Mark an arbitrary point on the x-axis and call it A. So we'll put it right there, and we're going to call this A. We'll put it right down there. And now mark a second arbitrary point, and we're going to call it A plus H. So we'll put it here. That is A plus H, and that point will be right there. You know what? Let's go ahead and give us a little bit more space to work with. Those are kind of close together. They don't necessarily have to be that close, just so we can make sure we can see what's going on. Okay, there we go. I like that much better. Okay, on the curve, mark the coordinates A and FA, right? This is an ordered pair. F of A is the y coordinate of x at A, or the function evaluated at A. So right here, this is A, comma, f of A, and then this point here, that is A plus H, f of A plus H, right? That's just the coordinates of each point. All right, so let's go ahead and mark these on the y-axis. So this is the point f of A, and then note right here, this is the point f of A plus H. Good. All right, so let's keep going. So we're going to go ahead and try and calculate the slope of the secant line. So let's go ahead and draw in the secant line, like so. All right, we've got a good secant line going right here. And so we want to calculate the rise over the run, right? So note that, this distance here, that's our run, right? That is our delta x. And know what this equals. This is A plus H minus A, right? The second one minus the first one. And when you evaluate that, you simply get H. Good. All right. So now let's take a look over here. And so we're going to calculate the delta y, right? That's the rise. Rise equals the delta y, and delta simply means change, right? The change in y, which is f of A plus H minus f of A. And that's, you can't reduce that because A plus H and A are both inside the parentheses, and so we don't know what f is doing to those parentheses because we're doing this in the general sense. All right, so let's go ahead and calculate the average slope, the slope of the secant line. We'll just call this average. The bar over the m means we're talking about an average. All right, so let's go ahead. This is rise over run, which is delta y over delta x. And now we plug everything in. That is f of A plus H minus f of A all divided by h. And that's our average slope. I believe in some texts I refer to this as the difference quotient formula. But it's just the average slope. It's the slope of the secant line. Like I said, a bunch of different words to describe exactly the same thing. And I don't want us to get too caught up on vocabulary and definitions. What I really want you to understand is how these guys work and where they come from. All right, so just a quick geometric example, a visual example, if you will, that we're going to use Desmos for. We're going to be plotting the equation y equals 5 times cosine of x, and then we'll be looking specifically at the tangent line that's passing through 0 and 5. We'll be zooming in to kind of see what's going on. Okay, so now we're in Desmos. We've got our guy graphed here. And again, we're focusing on the point 5 and 0. And so right now it looks like a nice, sharp, hard curve, right? There's no straight line going on here. But note what happens as we zoom in more and more. And it's really playing too much with the scale. I'm just moving into my fingers here. And what happens at this point here? That sharp curve that we saw, it's gone, right? It looks like a straight line. And so the point is that if you zoom in really close, all smooth curves will look like a straight line if you zoom in super close enough. I mean, for instance, we all know that the Earth is spherical, but when you look around, we all experience the Earth as just a flat plane. And that's just because the size of the sphere is so large compared to us that we don't notice the sphere. And so that's what's going on with this curve right here. You know, we're zoomed in so close to this one part that even though this has a very steep curve going on, if you move a little bit to the right or to the left, we're so close to it we don't see it at this point. And so again, every curve that is smooth, now if it's like a sharp jagged curve, it doesn't count. But every curve that is smooth will look like a straight line. And so we can kind of see that clearly at the point 5, 0. What is the slope of this tangent line? It's 0, right? Because it just looks like a straight horizontal line. And you know, if we zoomed in like this to other places, it may not be 0, but it certainly will begin to look like a straight horizontal line. So just pick a random spot real fast right here. Start moving in. Even though there is a curve, note that we get zoomed in so close, it looks like a straight line. And so that's what's going on when we use secant lines to approximate a tangent line, right? We bring those 2 points so close together that the line in between will approximate the curve. And so like it'll be an accurate representation at that point. So that's it for this video. If you have any questions, send me an email. Make sure you're staying on top of the homework on WebAssign. That is important, particularly for the pace of this class. You do not want to fall behind. Have a good day.